Warm, inviting. Have you ever looked at a perfectly smooth jet engine part and wondered how we make something that exact out of solid metal? We take the exact same approach a classical sculptor uses on marble. We start with a heavy, shapeless block and carve away everything that isn't the final part. Industry just scales this up into 4 highly controlled steps. Step 1 is choosing a process based on chip forming. That is the physical act of peeling away tiny ribbons of unwanted material to reveal the shape hiding inside. There is no magic to building these complex components. It comes down to a careful system of removing material. We can group these removal methods into families based on how they move. First are the rotators, like turning. Here we spin the metal itself against a sharp blade, stripping the outside to create perfectly round cylinders. Next are the carvers, like milling and drilling. Here, the metal sits completely still while a spinning tool pushes into it, carving out flat surfaces, deep pockets, or holes. Then we have the gear lakers. Methods like hobbing use specialized cutters designed specifically to carve out the precise interlocking teeth you see inside car transmissions. Finally, the polishers. Techniques like lapping, honing, and scraping remove microscopic amounts of material. They take a surface that is already flat and make it mirror smooth. Choosing between these depends on the job. A high-speed rotator is the best choice for mass-producing simple bolts, while an aerospace valve might require the slow, surgical precision of a polisher to reach its final shape. Step 2 focuses on the actual tools doing the cutting. A cutting tool works because of its geometry. The blade is ground at precise angles that allow it to slice through steel like a hot knife through wax. Look at a single-point tool used for turning cylinders. The top slope, called the rake angle, acts like a wedge to lift the metal away. The gap underneath, the relief angle, ensures the bottom of the tool doesn't drag and ruin the fresh surface. This diagram shows a multi-point tool, like a standard twist drill. The sharp edges at the bottom, the lips, do the actual cutting, while those spiral grooves, the flutes, act like tiny highways to carry the waste material up and out of the hole. Even a grinding wheel, which looks like a solid piece of stone, follows this rule. It is made of millions of microscopic sharp edges, taking tiny bites out of the metal. The precise geometry of these angles and edges determines exactly how well the metal shears away. Those tiny bites of waste material are called chips. By examining them, machinists can tell immediately if their angles and speeds are correct. This diagram illustrates a continuous chip. When cutting softer metals, the waste comes off in one long, unbroken ribbon. The metal can weld itself to the blade, creating a built-up edge that breaks off and leaves a rough surface. That is why we prefer what you see here, discontinuous chips. These are small, separate chunks that easily fall away from the cutting zone, keeping the blade clean and the operator safe. Seeing the small, consistent chips fall away is the physical proof that the cutting process is perfectly calibrated. Computer numerical control guides tools using a 3D grid mapped on X, Y, and Z axes. We set a work offset, anchoring the grid's 0 point to the metal block. Then, a tool offset adjusts coordinates for the blade's exact dimensions. Because these computer-guided movements happen so fast, friction generates immense heat. We flood the area with liquid coolant to keep the tools from melting and to wash those chips away from the cutting zone. Through exact coordinates and steady cooling, the machine turns an abstract digital design into a tangible physical object. Step 4 is verification. The most complex shape is completely useless if it misses the blueprint's dimensions by even a fraction of a hair. We use instruments like calipers that can detect a tiny gap. By lining up 2 different scales, we can spot a difference as small as 1/50th of a millimeter, much thinner than a human hair. For tricky angles, we use a tool called a sine bar. By lifting one end over precise blocks, it creates a physical right triangle, allowing us to use basic trigonometry to verify an angle standard tools cannot reach. We also check the trueness of the part. We make sure flat surfaces don't bow, and we test spinning parts to ensure they don't have a microscopic wobble that would cause them to vibrate or fail. This intense measuring process ensures the physical part actually lives up to the promise of the theoretical blueprint. Select the right process, define the tool's geometry, guide it with precise computer logic, and verify the dimensions. When all these variables perfectly align, the cutting blade shears effortlessly. This is machining, where exact math meets heavy metal. It is how we build the tools, engines, and structures that keep the modern world moving.